就业博览会网页查询，欢迎同学踊跃参加。
From then on, you can do it with gamma ray bursts. Now these are the gamma ray bursts with the observed redshifts, the spectroscopically observed redshifts. But you could use these EPKIs or correlation to put in many more bursts in there. So this has been done, and so you can then sort of do Hubble diagrams like these, plot the luminosity distance versus redshift, and you try to distinguish between a model, which is an open model or an accelerating model or a closed model. And the GRBs, they extend to higher redshifts, so they can help you in distinguishing that. And so Guirlande et al. And several others have done exercises like that. And you can constrain some parameters like the equation of state W naught, right? So pressure is W times the energy density, W naught times the energy density, so W naught versus omega matter. Get some parameters right. Of course, you do similar things with CMB and with supernova, okay? And those get, relations that are sometimes orthogonal to that. So these can be used to additionally to do that, to try to constrain those parameters better. And you can also do the same thing. So this was done with GRB data by Sermani et al. For the first derivative of the equation of state. Parameter W1, and then eventually you can, do these diagrams for omega lambda versus omega matter, and if you put in, if you just consider supernova and CMB and BAO and Hubble parameter, you get this thing which is without GRBs is the dashed line, with GRBs is the solid line. So you can sort of, tweak, you can sort of get the parameters maybe in a little different parameter range. The problem is that the GRB, these correlation functions that are used to make it a standard can will have a certain statistical noise. There is just you just have the variance, an intrinsic variance, which is sufficiently large that you don't get a better constraint using GRB than the constraints you already have from CMB and supernova and higher acoustic oscillation and so forth. So the GRBs are interesting because you can measure them out to higher redshifts, but most of the constraints of cosmological parameters can be done with redshifts up to z equals 2 or 3, or with various acoustic oscillations beyond that, the CMB and beyond that. So it turns out that they don't really add much to these kind of constraints. Maybe in the future with more data and higher statistics we might. Okay, so what about even higher redshifts, let's say 20 or 30? We can consider population 3 GRBs. The first generation of stars might have occurred at redshifts of 20 or so. Those first population of stars might have been very massive. There is some argument as to whether they were lower mass, but typically they're being considered to be very massive. And those stars, the core will collapse for sure to a black hole. It's so massive it has to collapse to a black hole. But the accretion disk will be too cool for having neutrino cooling. So the accretion disk will not be a thin disk, it will be a fat disk, an accretion torus, donut. And the accretion into the black hole then can twist up the magnetic fields, and you can get the Blandford-Snijek type of effect to generate a Poynting-dominated, a magnetic field-dominated jet. And so you can calculate what the luminosity, magnetic luminosity of the jet is from the Blandford-Snijek type of mechanism. And you find that the luminosities are of the order of 10 to the 52 ergs, which is pretty decent. and the typical accretion times in the observer frame are up to a day, 10 to the 5 seconds for redshift 20. So it would be a long duration burst, almost a day long, a very long burst. But luminosity is so these actually hertz per second, so the total energy is you see. And if these are magnetic jets, not much variance, then the emission is mainly electronic. We will have a photosphere, which is a pair annihilation photosphere, and you can calculate that that will have a typical spectrum peaking at 50 keV in the observer frame. And then the external shock will produce a synchrotron spectrum which peaks at a few keV, and a synchrotron self-quantum component at the 70 keV. So you might get spectra that look like these. At about 1 day in the observer frame, you have the photospheric component, synchrotron, and the inverse quantum component. Now the point is that these are very long duration bursts, so maybe 1 day. So a typical GRB detector responds to a fast rise of the flux. And this wouldn't be a fast rise of the flux. If it's so long, it would be a very slow rise of the flux. And so you can detect it only with the so-called image triggers. But image triggers are used by Swift and Fermi, so you could in principle detect these. So there are other cases where you include pair formation where the spectrum might be different, but in the end you get these various possibilities that look fairly attractive in terms of a possible target. So essentially you would have a low energy signal, infrared, that is visible with JWST. Then you'd have an X-ray signal and a GE signal. All right, so let me mention then what are all the various connections of the GRB to various things. So we talked about stellar collapse, jet and fireball physics, and then there are some other aspects. I'll talk later this afternoon about ultra energy cosmic rays, etc. Gravitational radiation I will not talk about, but binary neutron star is supposed to do interesting things for gravitational radiation, very strong gravitational wave sources. And then GRBs could have an effect on the early universe reionization, but it's not very strong. They're not, the thing is that they are rare, even though they're very luminous, they are rare. So the total energy input into the universe is not enormous. But one aspect I didn't mention, and is very speculative, is that it may have some effects in geophysics and perhaps in mass extinction. So consider what happens if a GRB goes off somewhere within sight of the Earth. Okay? And let's say at some very early period, some worthless dinosaur was looking at what might this do to him. So let's compare the rate of GRBs and the rate of supernova and their energetics. So throughout the universe, supernova occur at the rate of something like 10 to the 5 per day of the types. One C-types are maybe 1,000 to 10,000 per day. GRBs are much rarer, maybe 100 to 1,000 per day at most. Okay. The rate per galaxy of a GRB is 1 per 10,000 years, but the supernova occur a few every 100 years. So there are many more of them. The supernova, these are rare objects. The energy output is comparable in both, maybe 10 to the 51, 10 to the 52 ergs. But the big difference is that the photon energy of the GRBs is mainly GeV, whereas in the supernova it's mainly optical UV. And needless to say, these can be much more damaging photons than the optical UV photons. if you consider what could they do if a GRB went off, so suppose you have a 10 to the 53 EISO event at about 10 kiloparsecs, let's say at the galactic center. Then this would give you as much energy at the Earth in 10 seconds as the Sun. So in a sense, it would be the equivalent of a 200 megaton explosion in the atmosphere. You're getting about as much as the Sun does, 0.1 watts per square centimeters for 10 seconds, but you get it in MEV gamma rays, not in optical photons. So does these do much harm? Probably not. If you spread it over the whole surface of the Earth, the heat capacity of the Earth is fairly large, and the gamma rays get deposited high up in the atmosphere, they might do something to the chemistry of the upper atmosphere. Maybe they destroy some ozone, but it wouldn't be a terrible deal. It wouldn't be much worse than what the refrigerators do by putting out their sort of emissions. On the other hand, if okay, so that was at 10 kiloparsecs, but if one occurred within 1 kiloparsec, so at 10 kiloparsecs, the event per 10 gigayears is maybe 100 to 1,000, equivalent to 200 megatons, not much damage. But at 1 kiloparsec, it's 1 to 10 every 10 to the 10 years. So every 10 to the 10 or 10 to the 9 years, you get 1. And then it's equivalent to a 20,000 megaton explosion in the Earth atmosphere. And then you would kill all the ozone, and you'd have acid rain, and probably all animals with eyes would be blinded and have severe burns. So it would be unpleasant. And if it occurs at 0.1 kiloparsecs, then it's extremely rare, every 10 to the 12 or 10 to the 13 years, so it is not going to happen. But it would be a huge explosion, and you essentially kill all life. So it is speculated, although it's pure speculation, that maybe a GRB occurred somewhere in the galaxy, maybe somewhere in between that, and maybe that's what caused the extinction of the dinosaurs. The statistics more or less agree. Of course, there are other possible explanations, that the meteor crashed, and produced a big tidal wave and ejected a lot of dust into the atmosphere, which then covered the sun, and then the plants died, and then the dinosaurs died. So it is a possible scenario, but it's not necessarily the right scenario. Okay, so let me just conclude. So the outlook for the observational prospect for the high energy observations coupled with the low energy observations, they're encouraging. One is getting bursts now that have large photon statistics, and with more and more of them, the analysis and the comparison to models gets more and more strict. Theoretical issues are that we still cannot decide between baryonic versus magnetically dominated jets, and we don't have good tests of how to distinguish them. And we cannot decide yet whether a hadronic prompt emission is an important component of the prompt emission, or whether we can get away with just a pure electronic model. If the photospheres are the important spectral component, again, are they baryonic or magnetic, or the modified internal shocks, are they the better explanation? Then reconnection, is it the reconnection that accelerates the particles, or is it Fermi acceleration? Work it either way. And the cause of the MEV to GeV delays, we have put forward several plausible explanations, but we still don't know exactly which of those is the one that fits the best. It would be very nice to obtain TeV photon spectra. As you know, there are TeV ground air Cherenkov telescopes that are looking for GRBs. In the future CTA will start looking too. So far, the searches for GRBs at TeV energies haven't been successful, but if and when they're successful, I think they'll constrain models much better. And of course, neutrino observations will add a great deal. Next lecture, we'll talk about the possible implications of neutrino observations. All of these things will constrain the particle acceleration of the shock parameters and the compactness, magnetic field strength.
Questions? I have two questions. So first question is about the measuring distance with GRB. So in that case, do you choose a specific GRB, like long burst only or short burst only, or can be useful?
Well, the redshifts have been measured spectroscopically now for both short and long GRBs, but there are only 15 or 20 short GRBs with redshift, and there is something like almost 400 long GRBs with redshift. So there are much better sample of the long GRBs. For doing these indirect redshifts using the phenomenological correlation between EPIC and the ISO, again, there is much better statistics with the long bursts. They're the ones that are used.
So my second question is that for the neutrino observed by IceCube,
Yes.
some lines which could be physical or electronically.
Right.
So could GRB somehow fit those events with certain probability?
Yeah. Well, I'll talk about that this afternoon, but let me just anticipate that the PV neutrinos detected by IceCube, which they argue convincingly are astrophysical, they could be GRBs, but it's difficult to get the right flux. So even though it has been argued, but I think they're not GRBs, and I'll show you why. Because the calculations of the neutrino flux are okay in the higher, so they're okay for some things, but not for those particular objects. So I think it's different objects that are producing those PV neutrinos.
And for those lower energy ones, it's possible.
Well, for the lower energies, I think at lower energies we may be, we will eventually, I think we'll detect lower energy neutrinos, TeV neutrinos from GRBs. But at the moment, we're still not detecting them. So, but I'll talk about these more in detail.
Other questions? Then I have three questions, but then the next one, people may get it. Okay, this question is, you mentioned that except the synchrotron shock, there will be black body radiation that can be the photospheres. So this is related to the third question, are photospheres needed? So I wonder, because the burst occurs in very short time, can we have a thermal equivalent here? Thermal equivalent, you mentioned black body radiation. So what, by definition, we should have thermal equivalent. This is the burst occurring in such a short time. So
Yeah. Well, that is time for equilibration. You need to get the black body spectrum. Well, I mean, the thing is that the mean free path of the photon is so small compared to the size of the system that you do get good equilibration. The outflow starts when the gas is very dense, so it achieves its equilibrium then. And then as it expands, it retains a more or less thermal spectrum. And the reason you can fit a parallel spectrum is that the black body actually, the photons can get upscattered by relativistic electrons produced by these Elapson's collisions and all that. So you get a deformed non-thermal shape, but the peak remains more or less the characteristic black body peak.
if no further question, let's thank the speaker again.